All right, let's go ahead and take a look at the design process resource first so that we can learn about the design process. All right, this class is all about the design process. This class is about using a process to design solutions to problems. That's the elevator pitch for the class. That's the short version of what this class is all about. You're going to go through this class doing one of two things. Either getting tools in order to do that, learning 3D modeling, learning sketching, learning those different things, or going through the design process step by step in order to practice it under different conditions. Those are the primary two different things you're going to do in this class. So right up front here, the first thing we want to teach you is what is the design process that we use and how does it function. So let's take a look at the design process. A design process is a systematic problem-solving strategy with criteria and constraints used to develop many possible solutions to solve or satisfy human needs or wants, and then narrow down the possible solutions to one final choice. That's a design process in a nutshell. That's its purpose. Let's come up with lots of possibilities and then use a system to narrow those down to the best one that we can use to solve a problem. This is the design process that we're going to follow in this class. What's the first thing you notice about this design process? Not the first thing on the list. What's the first thing that jumps out to you about the design process?
It doesn't have to end.
It doesn't have an end. It doesn't have to end. I'm going to have you compare and contrast this design process with the old one we used to use, which is up here on the board. This one didn't have to end either, but it wasn't as obvious. Do you see this one goes from top to bottom? It's what we call linear. Do you see that? It has a line that kind of follows through it. This one does not. This one is circular. And you see it can continue around and around and around and around. That's what we call iterative. I used that word previously, right? To iterate, meaning to continue to do something over and over again until you get it right. And that's why this design process looks this way. There are 6 stages to the design process. That's not too many to remember. Define the problem, generate concepts, develop a solution, construct and test, evaluate the solution, and present the solution. Those are our 6 steps. Let's go through those 6 steps and see how we implement those in class. Number 1, define the problem. Problems exist everywhere, and they vary in their degree of complexity and importance. More complex problems require more effort to solve. More important problems have more urgency in their need for us to solve them. So when we define a problem, we need to look at a few questions. Who says it's a problem? That helps us to determine why are we solving it and under what conditions are we solving it? How urgent is this a problem? If the person saying it's a problem is ourselves, then we have some more information about why we're solving it. If it's a person in authority over us who's telling us that we have to solve it, that gives us more information as to how and under what conditions we're going to solve it. What are the needs and wants of the stakeholders? What's a stakeholder? Does anybody know what a stakeholder is? No? If you come across a word like this on my PLTW, again, you're virtual and you're reading through this, the word's going to be highlighted. Let's take a look. A stakeholder is an individual, group, or organization who may affect or be affected by or perceive itself to be affected by a decision, activity, or outcome of a project. So these are the people who are either going to affect the outcome or be affected by the outcome of this project. Let me give you an example. A few years back, we had a team that was working for a project for a design competition. And they wanted to design a freestanding water filtration system that was inexpensive and used recycled components or reused components that could be placed on trails locally. The idea was that this thing be placed out on trails. It would collect rainwater, automatically filter that rainwater, and keep it sanitary. And people who were on the trail could pump water from it into water bottles and have fresh water then to drink. Who are the stakeholders? Who might affect or be affected by the outcome of this project?
People who are on the trail.
People who might hike the trail. Okay, animals around might affect the project or be affected by it, certainly, both. And that might have been one that they didn't think about initially, right? But needed to think about, certainly. Who else?
All the people making the filtration.
Okay, the people who have to make it. Typically, we don't include them because the other ones have to think about this, but they're certainly involved, absolutely. Oh, wait, so are you saying the team that was designing this or the people who have to build it later?
I guess the team.
Okay.
I guess the team and maybe the people.
I would say both would be involved, certainly. What about the people who manage and maintain the trails? Right? If there's a Parks and Rec committee or a volunteer organization or whatever, typically there's people who are in charge of and maintain trails depending on the circumstances, right? It could be municipal, it could be on a larger scale, it just really depends. But they're involved, they might be affected by the fact that it exists and have to maintain it even, right? So you have to think about them. Do you want to give them the schematics? Tell them how to manage it? Are you going to ask them to maintain these things that they break down? You know, bad water in a thing that you're telling hikers is good water could cause a lot of problems. It does matter, doesn't it? And the last one is the people who are running the competition at the competition level. They have a stake in it too, because they have to judge it and be involved in that. And it has to meet their requirements as well. All of these are stakeholders, and all of that matters. Are there any prior solutions to the problem? This is key. This isn't cheating, and it's not any of those things. We want engineers to think about how were problems like this solved in the past. I had those engineers involved in that project research. How do hikers gather water? How do they carry water? How do they filter water now? Are there any freestanding filtration systems that exist on trails currently? What do they look like? Know what already exists so you're not repeating work that's already been done, but rather improving on it if it exists out there. Does that make sense? Is the problem worth solving? Has it been solved already out there to the point where anything you do is only going to overcomplicate it or make it worse? Or is it worth solving? Is it a problem that is too minor, that is not really something that needs to be solved? Consider that. Is the problem worth solving? And what are the specific criteria and constraints required to solve the problem? Criteria, constraints, two halves of the same coin. Criteria say what needs to be done in order to say this is solved. Under what conditions are we saying this problem is now done? Constraints say, what restrictions am I placing on this project? For that project I was mentioning before, all the materials had to be reused materials that a municipality could get without having to spend money on them. It had to be stuff that could sit freestanding out in the elements and not rust or fall apart and hurt people. Those are restrictions. A lot of times criteria and constraints overlap a little bit. We try to keep them separate so they can be clear. Here's how we know we're done. Here's what we can't do. Does that make sense? Two separate things. Prove your problem is valid and justified. Tell us why we can do it. Include multiple considerations for viewpoints. Include a description of the people who would benefit from it, and provide credible referenced sources. Generating concepts. Generating concepts is a process we go through where we brainstorm many different ideas. And in the initial stages of generate concepts, we want to have as many ideas as we possibly can so that we can have a lot to choose from to narrow down to the one best solution. We don't like to limit ourselves at this stage. We want to have a lot of ideas so we can then come up with what the best one might be, combine multiple solutions, and then come down to the best possible solution. If you only come up with 2 or 3 ideas, idea 7 or 8 might have been a better idea, but we didn't spend the time to think about it. So when we in this class go through brainstorming activities, and we'll talk about that when the time comes, I'm going to ask you to go beyond your typical comfort zone with brainstorming and thinking of ideas. To think of ideas that are outside the box and beyond what you would normally think about. To come up with lots and lots of ideas. So then we have more to narrow down from. It's often difficult to truly conclude this step of the process because you often could continue to brainstorm and research indefinitely and never know when you're done. Often we have to put arbitrary restrictions on this step and say, this is when you're done. You have a time limit, or you have a certain limit of number of ideas before you move on. You want to research the problem, and we go through this brainstorming solutions activity here a little later when we look into our activity where we're going to come up with multiple solutions for a problem about a week or so from now. You want to research the problem, brainstorm possible solutions, consider any additional design goals. Now that we've researched and come up with some ideas, it's possible that we've refined the problem a little bit and thought about some things we didn't think about initially, some concerns or some additional stuff that needs to be dealt with. For example, project I mentioned before. They initially wanted to collect rainwater, have a system within to purify it, and then pump to bring it out. They quickly realized that the purifying system was going to be complicated and difficult to keep the way that they wanted it to be. And so they added on that they wanted to have a filtration system built into the pump so that the water was purified and filtered as it was pumped into the hiker's bottle. So that you knew that the water, whatever it was like sitting in the cistern, it was purified and filtered the moment it went from the cistern into your bottle. And so you didn't have to worry too much about the condition of the water as it was sitting in there. And that was an additional design goal they added later as they brainstormed and researched. So then at the end of this step, we select and justify an approach. We come up with lots of different ideas, done lots of research, done lots of planning, spent some time arguing and debating over different things, looking at all our different approaches, combining multiple approaches. At the end of this stage, pick an approach, justify that approach, move forward with that approach. Step 3, develop a solution. Steps 3, 4, and 5 typically overlap. We don't typically just do them one at a time. But develop a solution, we're typically going to refine that idea and come up with how are we going to move forward with it. It's typically combined with step 4, where we're going to build a prototype and test it and see how it works. Developing solutions and building prototypes are core components to going through the design process as an engineer. You have to do it. Lots of different ways that we construct prototypes. There are many times physical things in the real world we build with our hands. We have a beautiful shop next door. We have tons of great materials here. We have 3D printers in the back that you will always have access to make things. Many times we'll build physical real prototypes here in the real world to test. There are other ways to test. We can do 3D models on Fusion 360 and test them that way and try to do stress testing, or depending on the kind of test you're doing, if you just want to see how it looks or how it fits together, you can do testing in a 3D world like that. We have virtual reality headsets. We have a bunch of these, and we're currently working on getting 5 desktops set up on the end there with VR. There's a lot of testing that you can do in a virtual reality world. You can't hold it, you can't smash it, you can't move it, but you can see it, you can walk around it, you can walk inside it, you can technically lift it up and hold it and look at it. Lots of things you can do in a virtual reality world. You can make it different colors or different materials and that kind of stuff. You can experience it in a virtual reality world not ever making it real. If it's something that you don't have the ability to make real here in our conditions, you could do it that way as well. So lots of ways to construct and test a prototype. Through that process, we gather data. We test, we get data. We analyze that data and we evaluate the solution. Does it meet our needs? We have specific criteria for here's what we want to be able to do. Remember, we did that earlier on. We met with that criteria. Does the solution we came up with meet the criteria and the needs that we had? This often is iterative. This specific set, 3, 4, 5, is often a mini circle of its own. If the solution doesn't meet our needs, we go back, develop a new solution, start to test a new prototype, evaluate. New solution, construct and test the prototype, evaluate. And we often have a little mini circle right within that where we go through and keep on doing that process until we get it right. And sometimes we'll even jump back up to generate concepts. This isn't working. Let's get some new ideas and come back through. So you don't have to go through the whole big circle to come back to the beginning. At any stage in this, you can jump back to previous steps and try things out again. It's what you call an iterative process where we can keep on going back and redoing things until we get it right. Does that make sense? We evaluate the solution's effectiveness, reflect on the design, redesign if necessary. When we're happy with the solution, when we know this solution solves the problem, meets our needs, fits the criteria and the constraints, we move forward to presenting the solution. Present the findings, document the project. What steps did we go through? Keep all your data. Keep your sketches. Keep your 3D models. Keep your prototypes. Keep your everything and present it all together as a final presentation to whoever you're presenting for. For example, the students who were making the hiking project brought that then to the committee for that competition and had a PowerPoint slideshow where they went through, here's the different steps we went through, here's the things that we tested, here's what worked, here's what didn't work, here's what we redid, here's what we retested, and went through the whole project. And they demonstrated all the different things they did because the person you're showing this to wants to see you followed up on your due diligence and you've accomplished what you're supposed to accomplish. These are your deliverables for the design process. A deliverable means a thing that you could turn in to show that you've done that step. Step 1, we make a design brief. A design brief is a paper that shows each of those different things that we look at for defining the problem. A lot of times, the design brief is actually a thing that I will give to you. Because a lot of times the problem will be defined by me and you'll be solving the problem. It's a pretty common process in this class. So many times that step 1 will be a thing I will give to you. Generate concepts. A design matrix, decision matrix. Also, lots of sketches, lots of writing out of ideas. A decision matrix is a tool that we use to make a decision about a thing for which we have multiple different options. There down here is a decision matrix template, and we'll go through a process for using a decision matrix later on in this project. Develop a solution, a graphical model. Lots of different types of graphical models exist. A 3D model in Fusion 360 is an example of a graphical model that you might use. You might also have a sketch on a piece of paper. That's a graphical model. Something that's visual, that shows the decision that you came to and the solution that you're going to make. They're often more than just a drawing. It could be a drawing with annotations and comments around it and different components broken out and showing how they work. That could be a graphical model. Again, a 3D model with all the components maybe blown up and broken out so you can see all the different components there too. A graphical model showing us how this final process is going to work. Prototype, the typical thing you would have for a deliverable would be the prototype, the working model that actually functions. For evaluate solutions, we want your project recommendations. Here's what worked, here's what didn't work, here's what we're doing moving forward. And then, of course, for the last part, you're doing your formal presentation. Here is our final presentation of the project, and here's how we're putting everything together. All right, so this is the design process. I went through this relatively quickly, hitting the highlights. The details are in there. If you need to reference it at any time, it's always available to you. This project's going to take you through a process of forming a team and doing an instant challenge, just like we did earlier this week. This instant challenge is a little bit different. Now, there's a couple of things you need to know. Number one, there's a whole bunch of materials that we're supposed to have that we do not have because Project Lead the Way is dealing with shipping delays and hasn't gotten us all the stuff we're supposed to have. So we're going to have to sub out some of these materials for other materials because we don't have everything we're supposed to have. We can manage that. We're going to have to. As we go in here, this list of materials is going to change based on what we have and don't have because they haven't gotten us everything yet. You're going to go through and complete this instant challenge here as a team next week. It's a quick one period again, like always. And then you're going to get your data. I'm not going to go through the whole instant challenge with you right now, but the basics are that you're making a device that can throw a thing across the room. Your data is going to be how far does that thing go. You're going to write that information down. Then we're going to represent that data on what's called a box plot. Let's come over here and take a look at a box plot. Okay. Often called a box and whisker plot. A box plot is a graphical way to show how data is distributed. Again, data, in your case, is going to be the distances that the thing that you're shooting has gone. So from my starting point, I've got 5 feet, 8 feet, 4 feet, 3 feet. How many different distances has it gone? You write those all down, and you're going to show them on a box plot. Box plots allow you to quickly get an idea of both the center and variability of data. As we get into statistics in this class, statistics are one way that engineers look at data and understand if something meets the requirements. Center and variability are the two most important types of data that we look at. Center of data tells me if I keep on shooting this thing, what is the most likely average place it's going to go? The center point of my data. So if I keep on firing this thing and I'm getting 5, 3, 2, 5, 6, 5, 7, 5, I'm looking at what is my most likely point I'm going to hit. Now, it's probably not going to hit that exact point. We often call that number average. In statistics, we call it mean. And actually, for a box plot, we're going to use the median, which is another way of finding the middle point of our data. And I'll walk you through finding the median in here and how to display it. Variability tells me how far apart are my data points. So it's interesting to find that middle point of my data. It tells me something. What's my most often hit point? But variability also tells me how reliable my data is. Do I have any hunters in here? Okay, hunters. When is it rifle, archery? What do you use? All right, sighting in a rifle. You do that? When you're doing it, you're looking at the distribution of your shots on the target after you start off. Do you want them like this, or do you want them like that, spread apart? Small distribution of holes in the paper, right? If you've got your target afterwards and you found they were spread wide apart, what does that tell you? I would actually argue that it tells you something is wrong with your gun. Because if you're shooting at the same point every time, but the bullets are going all over the place, it might not even be something with your sight. It could be something wrong with the gun because it's not consistently hitting the same point over and over again, right? Something's wrong there. Same thing's going to be true with the device you're making next week. Something's wrong with your device. If you're doing the same thing every time, but the thing that you're shooting off of it is going far, you're getting 15 and then 2 and then 30 and then 3. And if you're going all over the place, that's wide variability in data. Your data is spread apart widely, and that tells you something about your data. If your data is grouped tightly together, 3, 4, 3, 3.5, 4.5, 3, 4, tightly grouped data, that tells me something interesting. Yeah, the other guy hit 30 at one point, There's also hitting 2 a few times. You know, and it's widely variable, and there's no consistency, no ability to understand what they're going to do. Whereas if I'm hitting 3, 4, 3, 3, 4, 4, 3, 3, 4, and I want to hit 15, all I got to do is adjust my sight, right? And I can bring it into where I want it to be. And that's more consistency. So this plot tells me my median point. Where is that point that I'm most likely to hit? But this, with the box here, tells me also my variability. How variable, how spread apart is that data? So the box ends are placed at Q1 and Q3. So we place our minimum data, our maximum data. How far did we go? What was the least point of our data? We then do first quartile and third quartile of the data set. What does that mean? Okay. First quartile is the median of the lower half. So our median is, if I line up all my numbers in order, all the numbers of my data set in order, the median is the middle one. So I start chopping off numbers from the ends, and I find the one that's stuck in the middle. That's my median. So my first quartile is now I'm looking at the bottom half. I do the same thing. What's the median of the bottom half? Third quartile, same thing. Look at the top half and do the median of that data, find that number. And I mark those. So I get my maximum, my minimum, my median, and the median of the bottom half, median of the top half. And I mark the whole thing and make a graph. And that shows me how my data is spread. It's a quick thing to make, and it's a quick thing to look at to show me comparison of different things. I could take one of these for each device you guys are going to make next week, display them quickly on the board, and you'll be able to see like that whose device is more precise and whose is able to shoot farther very quickly. So we're going to make these next week with the data that you guys come up with. And it's going to walk you through in here how to make a plot, how to construct the plot, how to lay it out, and how different box plots look when you do them, how to compare them. We'll use this as a resource next week to lay out your data and to design comparisons between the different devices that you make. So it gives you an example, outliers. I'm not going to get into all this information right now. This is a resource for you next week to use when you go through to make these. I want you to have this available. I wanted to show you quickly what box plots look like.